Our next presenter is Dr. Mahbube Subhani from Deakin University, and the title of the presentation is Advanced Signal Processing and Machine Learning for Damage Detection of Wooden Structures.
Thanks, Govinda. Okay, good afternoon, everyone. I am Mahbube. I am working at Deakin University. So today I will be talking about detection of damage for these wooden structures. I will not go into too much details, but we have a lot of aging wooden poles. Almost all of them, most of them were installed in 1960s. So they're still in use. Now the challenge here is how can we detect the damage of these poles, and to what extent we can detect the damage. So there are different ways, of course, we can implement to detect the damage, and broadly speaking, these are divided into vibration-based and wave-based. Now there are trade-offs, what we can do with it. So if we want to detect very small damage, we need very high frequency that requires very high energy, which makes it impossible or difficult for a portable system to carry because it requires very high energy. On the other side, if we use vibration-based one, we can detect only very large damage, but it's very portable and easier to implement. So there's a trade-off now, which direction we should go. So we decided to do it in two stages. In the first stage, we will focus on vibration-based, so we will only know whether the structure is serviceable or not. We are not interested in the beginning to know the location of damage or severity of it. We just want to know whether there is it in serviceable condition or not. So more like screening. So this project was in collaboration with AusNet Services, and we collected data from 13 poles, and 8 of them were unserviceable, and 5 of them were serviceable. And this was the and this is the kind of portable system we developed, which we took there to collect this data. So briefly speaking, what we're trying to do is we're trying to find out what are the damage sensitive features we can use to detect the condition of these poles, and what type of machine learning algorithm we can use, because the variability here is significant, because timber is a natural material, the species vary, the material properties varies, the geography has significant effect on its material properties, so it does affect the features significantly as well. So we wanted to see how does the machine learning play part into this. And the last one is the imbalanced data set. We never get a balanced data set for machine learning because we cannot choose how many data we want from each species or in each geographical location. So we'll always have some imbalanced data set, and how can that affect our machine learning algorithm. I will not go into too much details on the proposed methodology, but what we are trying to do here that we want to process the signal in 3 steps. First, we use wavelet packet transform. We can consider that as more like a filtering technique. So we're only selecting the frequency you want to deal with. That's what we are trying to do in the first one. And then the last one, IMF, we are trying to see the frequency time domain signal in the same graph. So you want to know at what time, what frequency component was present. So this is just to show that what type of wavelet packet we use for filtering. There are a lot of wavelet packet, mother wavelets are available, so we need to select a one which is suitable for our signal. So we selected 24, and we found out bi-orthogonal 5.5 are the best one for our application, and we went with it. So we reconstructed the signal we obtained from the field. So this is some processed signal after wavelet packet transform, using this wavelet as the mother wavelet. And then this is where, after we implemented Hilbert-Huang transform, what we found, you can see this 5 IMF. And if you just look in the top one and the bottom one, what we are doing here, we are separating some of the vibration and wave properties of the pole. So here in the higher IMF, if you see this line is straight, that means this is the natural frequency of the pole. So we are actually detecting the natural frequency at a higher IMF. And this value here, which is lower IMF or the IMF1, is associated with higher frequency. So you can see it's around 1000. It's higher for timber, not for maybe steel or other structures. And this is a natural frequency, which is around 48 hertz. Now the question is, can we see a difference in IMF1 or IMF5 if there's a damage present in the pole? But before going to machine learning, we don't really need to extract feature. We can leave it to the machine learning algorithm to determine. But what we are trying to do, can we find at least one feature which kind of visually we can say, just looking into that feature, that there are damage present or not? So we found that there are 72 features, and there are more on that. But what we found a clear difference is the amplitude was affected by a damage. So even if I don't consider that 71 features, which we don't really know how do those features relate to damage, at least instantaneous amplitude, we found it to be quite significantly different if there are damage present in the pole. But then we also wanted to see that, okay, so that's just 1 out of 72, and then the other 71, we don't really know whether there is any correlation between damage or not. And we wanted to find out, okay, so if you have these 72 features, how many features are really important or contributing in making decisions? So we use this different data reduction scheme. So there's just 3 here. So one is the correlation heat map, PCA, and information gain. But just a brief summary of this, what we did in this data reduction scheme, for correlation heat map, we come down from 72 to 60 features. PCA gave us 30, and information gain said we can actually consider only 7 out of these 72 features to detect the damage. And then we selected 9 machine learning algorithms to see if there is any effect, because there are some algorithm which works very well for large data set and some works well for a small data set. So we wanted to see which is better suited for our application. And then these are the different scenarios. Briefly, summary of this scenario is considering all 72 features, 30 features, 7 features, and SMOT is for imbalanced data set. So if we have more data related to say serviceable and less data related to unserviceable, what is the effect of that imbalanced data set? And if we use SMOT, which is a technique to balance the data set, whether it has any implication. Now, if you look into the right side, scenario 4, which for some reason it's not showing, but mainly what it is showing that this is dealing with 30 features, and the left one is dealing with 72 features. So you can see having more features doesn't always yield very good results, because here it's very clear that the results are better if we look into 30 features which are very much associated with the damage. If you just look into the top one, which is F1 score, which is a very good indication of the classification or the efficacy of the machine learning algorithm system, instead of just looking into accuracy, those values are quite high, which is not the case when we had 72 features. Now, if we look into another features aspect of that's called AUC, area under the curve. So if it's 1, that means the machine learning algorithm or the classifier is very good. And you can see that with only 7 features out of these 72 can have a very good outcome in terms of detecting damage. So we got almost close to 1 in few cases. I mean, of course, there are few. It's almost impossible to get 100% accuracy for timber. I mean, it's not possible. But we get quite good results, and that reduces our computational efforts quite significantly, because it's just 7 out of 72. And then this is considering another scenario. So these 12 features is just I selected as based on my experience, just to see whether I am better than the classifier or not. Yeah, because I've been working on this project for almost, that was my PhD with Jianchun, Bijan, and Uli. So I thought, okay, I select 12 features out of the 72 and see whether the results are a bit better or not. It's close. So I got best was 86.86 as opposed to here, where KNN got 0.95. But I mean, experience helps sometimes, I guess, in terms of selecting features or damage. This is just a summary of how, for different cases or different scenarios, these 9 classifiers performed. So the top 2 or 3 for each scenarios. So generally speaking, if we just look into the last one, the orange one, that's I think summarizing the F1 score. So 1 means very good. So for you can see that the imbalanced data set doesn't really have a significant effect. So that's scenario 3, 5, and 7, where we use balancing the data set. So we found, of course, there are some improvement, but I guess it's a judgment call whether we really need that a little bit extra accuracy or performance or not. And then the fourth one, which is the most optimum one, because it requires less data, less features to detect the damage. But generally speaking, we found linear regression and random forest, these 2 classifiers are working quite well for our application. Yeah. Thank you.
Thank you, Mahbube. Any questions?
Great presentation. I'm Amin from Queensland Rail, and we happen to have quite a few timber structures in our network, and our inspectors are pretty good in finding defects when it comes to timber structures. So my question is, and believe me, I understand what you've done is very complex, very good, but if we can find defects with a simple hammer, then why would we do this? Because if this one, for example, if it's good enough to detect very small defects, but we don't really care about them, because small defects are not going to cause any issues. And if the defect is very big, then you should be able to pick it up with a hammer, like a simple hammer hitting on the timber, and just listening to it, you'd be able to pick it up. So
yeah, I guess you need to have access to use hammer, though. You need to access to the location. So if it's a 12-meter long pole, you cannot access to the top to use hammer.
Yeah, and that's my second question. Do you need to move the probes to pick up the data?
No.
Okay.
So that stays there. And it's also not subjective to the experienced operator, right? So there is no subjectivity into it. So it's the idea is to use it by layperson, just to know, kind of a traffic tier system, that is it red, green, or yellow. So that's, I mean, of course, often we found that experienced people might have better prediction, but to say that, I mean, you will always not get that many experienced people, and especially when you have, hundreds of thousands of this type of structures. And not all the time you will have damages where you have access to it. There are places where you don't have access. Yeah.
Perfect. Thank you.
Aris, you had a question? Yeah.
Interesting presentation. Just I want to understand, did you have a verification on the defined damage on the structure, or you knew the damage and did you verify that? Because when I was looking at your test data, it's like using the varpation data. So it's a high frequency, and then you're using the amplitude, for instance, and you don't have the mass distribution, and it can depend on the source. You can get different amplitude and different under stiffness. So this is the first question. Second is that when you're using a PCA, principal component, so did you come up with any issue with normalization? Because the high frequency data it's very difficult to use PCA. So I appreciate if you can explain. Thanks.
Yes. So the first one we did normalize the hammer impact because it could be, for example, when we had these results. But actually now we are trying to get rid of hammer because to reduce that subjectivity as well, we are now having a controlled input. So this amplitude, whenever we are considering amplitude as a feature, we have to normalize because someone can hit harder and someone can hit. So of course that was normalized. In terms of principal component analysis, here, so what we did, it's not exactly the high frequency. It's, for example, so these are the features we consider for PCA.
Yep.
Yeah, it's not the frequency itself. Yeah.
Just did you have the very part the detect the defined damage?
Yeah. That's a very good question because for unserviceable poly, yes, because they are planning to get it out, so we could verify those are really unserviceable. But the one which was serviceable, that was in service, so we couldn't take it out. So it's possible there could be some damage in those ones. That we don't know, to be honest, yeah.
It's David first. Maybe that's it with the last question.
So,
if you want to discuss further, maybe we can just continue later. But the last question.
Yes. So very quickly, I was curious on the. So you use the IMF, so the HHD as a decomposition band, but that technique doesn't allow you to control what frequency content goes where. And so how do you normalize, or how do you ensure that you always have the same basis?
Yeah. So now there is another so not IMF, I think that's called VMF, where you can control how many level you want, but we didn't do it. I mean, what we did is we used this wavelet packet transform before we put it to Hilbert-Huang, so that we get 5 IMF. Yeah.
There's a lot of discussion. I think in the interest of time, like please ask questions at the networking sort of session after this. But thank you very much for your presentation. There's a lot of very rich discussion.